discussing Bechamel and building up foundations, discussing the case when you just have a finite MVP with S states, A actions, planning horizon of H in a discounted setting. So that is 1 over 1 minus gamma. And there are two cases to discuss. One is when it's a bit unreal. You can sample next states and reward slowing transition at any state action pair of your will. We call that Z design, YZ, I don't know, running out of letters. And Z is sometimes the state action pairs. So you can choose a state action pair at your will. It's like basically the same thing as with simulations, except it's passive. It's like you have to decide ahead of time how many samples you want to get at each of the state action pairs. You can get those samples, collect them, and then you need to estimate a policy. And so let's say your output is pi hat, then you care about how much is lost compared to the optimal value by this policy. So if you can bound the L-infinite norm of this, then we'll be happy. Equivalently, we're asking the question of how many samples do we need altogether? How many of these little snippets do we need such that the error is below level delta? So for delta suboptimality. So here you might ask a question about like, oh, how does this depend on M? And so that's one of the settings. The other setting is policy-based design or policy-induced data. So in this case, you can't choose these state action pairs, but maybe you're given an initial state or an initial distribution over the states. And you can choose a policy, which we usually call the behavior policy or the logging policy. There are different names that you can use. And you can generate trajectories. So M trajectories of some length. It's probably not worth going over the planning horizon quite much. And altogether, you're going to collect a number of samples, and then the question is the same. Given the samples, choose a policy, how close this is to optimum, and how many trajectories of a certain length, or how many total transitions you need to generate in order to achieve some target level of suboptimality. And so for the first question is, okay, so this Z design calls for determining how many observations do we want for each and individual state action pairs? One can feel that because of symmetry a priori, there is no reason to collect more samples at one state action pair than for another one. So all the clever algorithms are going to collect an equal number of observations per state action pair, because there is no feedback here. And clearly the number of samples is going to scale necessarily with the number of state action pairs. The question is, how does it scale with that? How does it scale with also this target suboptimality and the horizon? And for this, we have this theorem. For Z design, SA times H cubed over delta squared samples are sufficient to get data optima policy. And in particular, uniform sampling, yes.
This term Z design, is this like a term from statistics, or are you just using it because
I just made it up. Like I don't know what to call it. It's completely my thinking.
Okay.
Yeah.
And then just a slight side note, when we talked about G optimal design, is that term G in the front, is that specific?
That's standard.
That's
in
standard.
Statistics, yeah.
And does G stand for something?
What was it? Like, so there is this big theorem of Kiefer and Wolfowitz that says that G optima design and D optima design are the same. So D optima stands for maximizing the determinant of design matrix. That's for the determinant.
Mm-hmm.
The G, that eludes me more now. It was, yeah, some really unimaginative naming like the Z design, I think.
Right.
I think I read it somewhere that they were like going through the letters of the alphabet at one point.
Right, and that term optimal before design, is that like, would that be more viable to put in here? Like, I don't know, I'm just wondering about the like naming.
Yeah, so we could say that the optima design for this problem would be the uniform policy. And you can prove that. And no design can do better than that. So we could say that optima design is the uniform it's not, okay, call it sampling. It's like you need to ask for the same number of samples at each state action pair. So that's one side result, and a second side result is that given the data collected, plug in gives. Okay, this part of the term cannot say that this is optimal, because we don't know that. So the design to be chosen is the uniform sampling, and plugin gives the data optimal policy, the plugin rule. And the second part is that this is best possible. Up to log factors. Because there is this tilde which hides some log factors. You don't know whether you can remove the log factors and share it. Someone sooner or later is going to answer this question.
So you erase the optimal because of the log factors, right?
Yeah. But regarding your question of the optimality of the design, I think like regardless of that, you can argue by symmetry that it has to be optimal. So I think that there is a simple argument to be made about that, that you don't even have to know how you do the rest of the things because of symmetry. It cannot be that. Since you have complete lack of knowledge of what the MDP is, you cannot possibly be thinking that you want to get more observations at a particular sample state action pair than at another one. So, and you can make that rigorous. It's not too hard. So for sure the uniform sampling is optimal. And plugin gives that optimal, the optimal result up to a log factor. And no, we don't know whether the log factors can be removed. So that's pretty much everything about this set design. And the last time I talked a little bit about how you could, the different proof strategies, you could try to prove some suboptimality results for the plugin rule, or for that matter, any other rule. And there are different paths that you can take. If you choose a very simple path, then you get h to the power of 6. You can improve that by just focusing on this, like using the value difference identity that removes an h squared. And then you still have h to the power of 4, and you can remove a final h by replacing, there is a Hovding's inequality used somewhere. And if you, instead of that, you use a Bernstein's inequality, and you're really careful about what you need to bound. So you have to be super careful there, because the variance itself that comes in Bernstein's inequality. So you know the difference between Bernstein and Hovding, that Bernstein allows you to exploit low variance. But the variance itself of the terms that you need to bound are not necessarily small, but they are pre-multiplied with some matrix, and the pre-multiplied expression itself cannot have a too large of an infinity norm. And so that's kind of a very beautiful observation that comes from a paper from around 10 years ago. And so that kind of shows that, okay, there were key things here, Bernstein, and we see it, that this value difference identity, which is very simple, it is just using almost definitions and then some rearrangement, and avoiding more contraction arguments. So kind of like pushing out contraction arguments to as late as possible, or avoiding them, and bounding terms before, which kind of makes sense. So these are the ones that were key to achieve this result. So that's Z design. For the policy-based designs, we have a similar result. A little bit more disappointing. I don't know about the two other. That is okay. So the main term here is something like the minimum of Asian, what was it? S minus 1, something like that. And then a poly term in SA over that squared. So this is how many total transitions you need to generate. And then the plugin So this many samples are sufficient for that optima policy, and the design is going to be the uniform sampling policy. Again, you can argue by symmetry that you can't do better than that. So the uniform sampling policy in each state chooses an action uniformly at random. And again, pi hat can be computed using the plug-in rule. And this is essentially optimal. So can't do better than the same expression. I should write maybe the omega in the exponent because there is some minor variation there with H and S. But it's a really small difference. So contrasting the two results, the difference is striking. If you can only generate samples from a policy, things are really, really bad. Basically, you need exponentially many samples in the worst case sense. Still, the same algorithm works. Plug in simple enough and doesn't seem to lose much ever. By the way, interesting historical tidbit. There was a time when somehow historically people first proved results like this for model-free algorithms, and there were speculations about that model-free algorithms, because they don't need to estimate models, are inherently better. And that speculation was going like this. Even transition probabilities, if you need to write down them, you need S squared times A entries for that, right? For every state action pair, we have S possible next states, so that's S squared A. And if you look at the sample complexity here, so here it makes no difference. But here, in the upper bound, you have a linear dependence on the number of state action pairs. And people were like, oh yeah, model-free algorithms that only need to estimate Q functions or action value, or the optimal action value function. And you can write down that as a table with SA entries, so that kind of makes sense. That it saves on a model-based, but basically by being clever about how you're proving things, that additional, so initially, like it's really easy to get S squared A and even H to the power of 4 over that squared. And you need much more work. Oh, so here I didn't actually say another key technique is this, that you have to deal with random value functions, and the covering argument is needed for that. And the key to avoid the additional S dependence with the covering argument is to introduce like a very clever technique which focuses on that when you have the terms that you need to bound, they look like this, and then you need a covering maybe for this V, because this V is random. And so if you do a covering argument there, then you would suffer in the complexity bound an additional S. And they're saying that, but this is going to be pre-multiplied with some mu, and because of that, somehow you can avoid all of this and then push this additional S dependence into a higher order term. So that's called the absorbing MDP construction. So all of these three things were needed, and the field needed like 10 years to kind of figure it out. That all of these three things are needed. It's just interesting historical tidbit. So model-free algorithms have absolutely no advantage. Maybe you could have expected, but it was not trivial to actually get there. Yeah.
I guess they have no advantage up to log factors, right?
We don't know the log factors for any of them. And actually, the model-free algorithms seem to be worse quite a bit, like empirically, most of the time. So it's like, it's probably the other way around. It's okay, so I think that the general lesson here is that, okay, it was hard to get this result, and people were, okay, so the first thought would be, no, it's like model-based should be the best. Then it's hard to get that result, and then some clever folks figure out the better result for the model-free. So that creates an interesting situation. Should you be betting against then the model-based method? I'm like, there are these heuristic explanations about it, but to me it was never too convincing, because we know that you don't actually need to estimate the full transition kernel. You only need these averages, and you could expect that if Q-learning or these model-free algorithms can somehow make things work, then it would be quite unexpected that the model-based algorithms would just like be broken by design, by their design. They're not. And so maybe if someone or people are making a surprising statement, then even if there are some heuristic explanations of why that is true, just remain skeptical. Yeah?
In the policy-based design, are we constrained to sample trajectories of a certain length?
No. You're not allowed to adapt the lengths of the trajectories, but it has to be passively chosen ahead of time, but you can choose it in some fixed way.
The bound shouldn't depend on that length?
No, it's the total number of samples, so it's like n times n.
If the length, for example, is 1, and I take the initial distribution as...
Oh, this is for the optimum length. It's like with the best possible length. Okay, so I should say that the design uses the uniform policy with lengths, something like h over the squared or something like that. No. It's more like look over that. Yeah. It's just a contraction argument.
The optimal length?
That's the optimal length.
Up
to a log factor.
To optimize what?
To get the best sample complexity.
Okay,
You achieve this sample complexity with this length. You two log factors you can't do better.
But if the length were 1 and I'm sampling from uniform distribution,
Right, that's really bad.
For uniform policy, that wouldn't be the same thing as the other
Right.
case.
Yeah. So here, either you have an arbitrary initial state or arbitrary initial distribution. So this result is a worst case over this. So if your initial distribution concentrates on a single state, and your sampling trajectory is of length 1, then you learn everything about what happens at that state, but nothing else. Of course, you want to learn about the other states. So here, the real challenge is that you want to learn not only about the states that come from the initial state distribution, and if we allow the initial state distribution to be chosen by us, then we're back to Z design. So maybe that's what you want to point out gently, that's a relationship that exists between the two. But here, what is being considered is someone else chooses the initial state distribution, and despite that choice, you want to do the best. Because most of the time in applications, you won't be able to control that. Yeah. Good. So yes, in this case, as you could see in the notes, the hard example is indeed one. When you have an initial state, you have a long chain, and you really have to go to the end to see whether you want to go to the end or not. And if you're sampling from the uniform policy, you can arrange things such that it takes exponential time to get to the end. It's really easy to see that. And the plugin rule actually gets this, okay, it's some calculation, but it's not super surprising. It's not completely trivial because this bond, sorry, it's, yeah, here. So this bond depends on, you know, a polynomial, like this exponential term and then like not double exponential, not worse or not unbounded. Like it could have been that there is a state which has a very small access probability under any policy, but then that state doesn't matter, right? So it's like the smallest probability that you will ever see of reaching some state from the initial state distribution plays no role. So that's an interesting tidbit here. And it should play no role because if that particular state has such a small probability of being reached, then of course its contribution to the value cannot be much, right? So if one does the analysis in the appropriate way, then this small probability should not play a role. So there are a few other things to discuss. So since we're talking about these small probabilities, so there is this question of, there are a bunch of results in the literature where the results are expressed in terms of these probabilities. Or something like this. And then the question is, do you really want to have those results? Why would you want to do this? So that's one discussion point. Another discussion point is that in the literature, you see a lot the pessimistic algorithm or plugin method. And so that's the bigger question of whether there are real differences between various algorithms that you can come up with. Given that you have some worst case results, but like maybe there are some finite distinctions to be made between the algorithms. So regarding the first, so these papers that introduce bounds where you see these inverse probabilities popping up. So on one hand, this can be much worse than even this, because this probability can be really small. On the other hand, they could be better than this if the smallest probability is actually large. So, so you can take the minimum of the two bounds and then that gives you maybe a more complete picture, and maybe that's why you want to have bounds like this. Also, people ask different questions as well, not only this finite sample oriented worst case questions. They ask the question, okay, asymptotically, in the limit of large number of samples, what's the best possible that you can do, how to squeeze the most out of your data. So they do this asymptotic analysis, and for that you will see quantities like this actually popping up in the lower bound. Because asymptotically these quantities are controlling how well you're estimating, I don't know, values, or like the optimal value at an initial state, or like how well you can estimate the optimal policy or compute the optimal policy. So it's kind of an interesting phenomenon then. If you're fixing one instance or a class of instances where these probabilities are controlled, then these quantities can show up in lower bounds despite the fact that you have a uniform upper bound where this quantity doesn't show. But that's worst case finite sample bound, and this is asymptotic and instance dependent or semi-instance dependent bound. Sometimes it's like not the full instance is controlled, but some aspects of the instance. Yes?
Yeah, I just had a kind of discussion point about the previous result. It's interesting for a lot of these like lower bound results, the issue arises with these like horizons being long, that we can plant this needle, and then we have to sample all these long trajectories. And like, if one claims that maybe we just have small horizon problems and this is polynomial, right?
Yeah.
And yeah, it's just interesting that like before for the tensor plan case, we claim like, oh, this is actually an okay result because we can have small actions, and then that's polynomial. But then like for something like this, we state that this is bad.
No, we shouldn't, right? Like
Right.
it is what it is.
Yeah.
So my take on all of this is that, well, we're just exploring the landscape, and we
Right.
found that this is what's happening.
Yeah.
So this also tells us that if you want to have some success, then maybe one way of guaranteeing some success is to look at problems with small horizons.
Mm-hmm.
A horizon of 2 or 3, maybe 5 is doable, maybe 10, it depends on the situation completely. This just tells you that, okay, hang on for a second, if you have a long horizon and you have a large number of states, then you might run into trouble. Doesn't necessarily mean that you will.
Mm-hmm.
It's just that you can't claim to be able to do all of these things for those problems. So that hope is gone. But yeah, I guess it relates to Gabor was asking a question on Slack.
Yeah, I wasn't really sure why people look into these problems if we have this kind of result. Wouldn't it be better like to maybe in the cases when we can change the policy a bit, wouldn't it be better to come up with some sort of a guarantee that if we just explore a little bit, then the companies will lose not so much money? Like, is there some sort of result in this?
Yeah, there are results in this direction as well. I guess you were asking the question a little bit more pointed way on Slack. You were asking why do they keep funding research where people are just looking at batch algorithms, right? So we see a bunch of papers coming out of all the industry labs. Well, first of all, companies are like these days they're just running these research labs, and it's curiosity driven. So it's not necessarily tied to their bottom line of what the researchers are doing. There are many steps away from the applications. So the same way as in academia, you are asking these questions. They are still asking the questions, although many times there is some optimistic upshot to these papers, as if like, oh, look how much we can do with batch RL, right? Like there are a bunch of those papers. But I think it's unrelated to whether it's done in companies or people just don't want to give up. The companies, yeah, they fund research. But to the follow-up question that you had, whether there could be better questions. And it's usually like, okay, so if we allow some sort of interaction, we can do much better, right? So one of the things you can do is that you start with a small sample size, you run your thing, you estimate your MDP, and based on that, you come up with a better policy, and then you keep doing that. How should you be doing that if you care about getting a good policy at the end? So that's online interactive learning that comes at the end. The answer is the exact opposite. Usually don't be pessimistic, because if you're pessimistic about what's going to happen, then you're not going to keep an open mind to the possibilities that could have been happening or could be happening, and you miss an opportunity. So you will pay an opportunity cost. So that, okay, so to me this, like it somehow relates to this, it's kind of interesting, this duality between this pessimism and optimism. So if you care about keep improving your policy, and you have the view that you're running the current policy for the sake of improving in the future, then the pessimistic choice is the worst possible one. It's horrible. And so you can make that rigorous, right? So it can get stuck. Because, for example, imagine that you just have a sleep-bandit problem. You have two actions. Action 1 is optimal, action B is suboptimal. But action B has a deterministic payoff. Action A has a stochastic payoff. And you start badly with that. Then if you're pessimistic about it, you will never ever learn that this was actually a better choice. You just stick to your worst choice. It's interesting that psychologists researching animal learning and human learning find that animals and humans are optimistic to some degree in these situations when there is an opportunity for learning. So there is even a book written by a psychologist about it. So Mother Nature maybe also discovered optimism. I don't know how strong the evidence, but like it was independent research. They didn't know about all this literature in machine learning about optimism. They were just like looking at the data, and they were like, wow, okay, like these animals are really optimistic about their options here when they are making choices. So it's kind of interesting. And so being interactive, that's an option. And you have many options there. So if you're a company and you're kind of risk averse and you don't like wide optimistic exploration, then you can limit exploration in various ways. And people have been looking at that. Still, why look at the pure case? Well, it's just a pure case, so it's good to have some corner points, I guess. And the hope never dies, and they are also hoping that they are not in a worst case setting, which is, yeah. I think it's okay to hope for that, but maybe you should make an attempt to verify whether that's the case or not, right? I also remember talking to Warren Powell. At one point, he was like, I was trying to verify how good these policies are. He's an OR person. He wrote some books about approximate dynamic programming, beating curses of dimensionality, whatnot. And so he's an OR person. He's interested in OR problems. And in some OR problems, you can explicitly compute what the optimal policy would do. And then you can back check what, like your favorite ADP algorithm would do. And he was telling me that it's very disappointing to do this, especially with batch data. So, yeah, you have to scale your expectations. Yes.
So batch bandits, though, good idea.
Well, okay. Explain.
Lower
Horizon
bound
1?
scale- Yeah, lower bound scales with the number of actions.
Yeah, Horizon 1.
Yeah.
Yeah, it seems, so that's kind of the story. It's like, oh, it's not only the horizon, it's the number of states or the horizon.
Yeah.
If one of them is small, you're good. By the way, here the number of states should really be taken as, like somehow the size of the problem, right? Like it just, you can I'm sure that you can generalize all of these results to, parametric settings where it's not the number of states that matters. It's really how many degrees of freedom you have in a way.
The reason I guess I asked this is take your RL problem, make it a policy search problem. The number of actions is the number of policies. And then maybe you have some good way of compressing this thing. Maybe you have some good approximation.
This is the number of places, a to the power of h.
But your bandit problem.
Huh?
Okay. Oh yeah.
Or a to the number of s. That's the number, but like you can take the mean of the two. So this is basically the number of policies.
I guess maybe I bring this up as okay. Maybe we want to do some function approximation, and it's like a to some dh or something. We have function approximation.
Yeah, that could be it. It's interesting though that this is not really SA, but just S.
Yeah.
So it's like, okay, I said it's like the number of parameters, but like, no, not really. It's more like you really do have this notion of state of like the different places that you could be at, and like somehow you need to measure like how big is that. But if you had some continuous state space problem, but there is some smoothness to it, then okay, you can replace that with a covering number.
Maybe I'm also imagining like everything is tabular, but you have some approximation just for the policy space, and the number of policies itself is small. Like the number of policies itself is small because you have function approximation or compression on the policies. Does that make sense?
Yeah, and there is indeed a paper about that. Yes, so this is, I think it's Kernson saying, so in a paper where they're talking about policy search, or maybe Hank, I don't know. These were all at the same time. Basically, if you have an MDP and you have a small set of policies, and from this small set of policies you want to choose the best, then you can imagine that you just run some simulations with the MDP. Okay, so that, like, in their paper, they're in between these two. Because they're not going to just run a simulation with a single logging policy, so it's not really batch in that sense. They'll build a tree. And then once you have a tree, in the tree you're just branching based on the actions, right? So it's almost like uniform policy. though, I guess. But wherever you get, so it's like the sparse sampling algorithm. Wherever you get, whatever state you get, there you're trying all the actions, you build a tree, and then you can simultaneously evaluate all the policies. And here the yeah, so if you build this tree, I guess the tree is still exponentially large, so it's not super interesting. You could just like run a trajectory of a single policy and compute probability ratios. So with impedance weighting. But then this smallest probabilities would come in, and that's a little bit of a letdown.
Maybe, I was going to ask, maybe you have an assumption that you have an oracle that tells you if two policies are epsilon close. And then the question being like, okay, you might have certain MDPs where you actually do have a lot of policies, but imagine that there's a chain and there's a rewarder one at the end. So all policies are pretty much the same except for the policy that goes all the way, that places non-zero probability on going to the last state. Like you can almost like separate them just by doing this.
Okay.
And maybe the number of actions are two. You either choose a policy and the bin where you place.
How does this relate to your topic?
Oh, just like the number of policies being small.
Yeah. So I buy that. Okay, so maybe you choose a policy space, and then you're hoping
because you then said the number of policies is still
that
like A to the HS, and then okay, maybe.
that a sample complexity of this size would be enough. And I think that's maybe there is an extra SA or something. No. How was it? Like they were building a tree. Somehow I think that they get this result. But that's a valid question. But right. Oh, okay. So I think it's ang, and it's Pegasus or something, which is an abbreviation of something, I don't know. And it's for a subset. Okay, the core idea is this common random number generation. So sometimes you can write the stochastic dynamics. Sorry, you can always write the dynamics in this form. Like psi would be an IID, I don't know, choice. Like that's a uniformly random on the 0-1 interval. That's regardless what MDP you studied, you can always find a depth such that the distribution of the next state follows the desired distribution given any state action pair that you start from. And they say that if you have access to this F, then you can be clever. Because, and they ask a different question. It is very sticky. It is not how many samples you generate, but how many excites you need to generate. And then, okay, so how much randomness do you need? And you can reduce the amount of randomness by recycling the randomness, right? So the same randomness, so the same sequence of excites can be used to to evaluate any number of policies, and the price for that is just logarithmic in the number of policies. Right? So if I generate okay, so there is going to be two indices. T is going along a trajectory, and so maybe it goes up to h times log 1 over delta, and I is like how many repetitions we have, and we have n of them, and you generate this table in an IID fashion. Okay, so the total number of random generator cores is n times h log 1 over delta. Delta is your target accuracy for the policy. Yes?
Sorry. Is the random number generating the bottleneck here? I didn't.
Yeah, it's not. But they are still answering this question. It could be that the random generator is somehow very, very slow or something, but usually it's not really the case. But nevertheless, I'm just explaining what they do in the paper.
Okay, so I'm just wondering how this number of random number generations became interesting.
We can start the discussion here, sure. This paper was published at ICML, got good reviews. I mean, it's okay, it's kind of cute,
Yeah,
but I'm totally with you. I don't really understand, like, what is the big savings here? Because you will still need to run the the simulator. So basically what you're gonna do is that you have access to apps. So, it's absolutely not batch. Because you have access to app, and the actions are going to be selected based on whatever the policy is, and then it is just that, like, here you can recycle the randomness and don't need to use private randomness for evaluating all the policies. So you can share the randomness between the policies, and then you're still fine. You just need a union bound to deal with that. So the cost is going to be logarithmic. Yeah, I'm just trying to remember, like, this jungle of all these papers, because they looked at this policy search question. They were not clearly asking batch RL or whatnot, but it's always somewhat close. So this is not that. There are the cases where you need to use this probability ratios, but we know that with this probability ratio, so what is this probability ratio business? You can do it in many different ways. So if you're generating data from a logging policy, and you have a target policy to evaluate, then the value of the target policy, some state S, is going to be the expected value in that MDP if you are running this target policy, and then sum up all the rewards. And you can rewrite this by taking the ratio of the marginals so here I want to change to the measure that is generated under the logging policy. So this is the difference, this is the logging policy, and since I introduced the logging policy here, and I want the target policy, so here I need to introduce the marginal probability don't know, seeing some state action pair divided by the marginal probability of that seeing under the logging policy. So we are basically canceling that this was generated from this. And then the big question is whether this is going to be controlled. And most of the time it's not controlled. Some people write things in terms of this, these ratios and push these quantities through. And if you have a finitely many policies to avoid, then maybe you can bring in a log pi again. So that you definitely can do. You only need to pay a logarithmic price for having a large number of policies, but that's not really the main issue here. The main issue is this density ratios or probability ratios, that they can very quickly diverge. Actually, okay, so this is what I wanted to say. If you have these probability ratios, on expectation, these probability ratios are of course 1 because that's how they are defined. And so when people say that they are diverging, so how does that happen? So it kind of happens in a very funny way. So occasionally, with very small probability, you would have a large value, but typically you will have a very small value. So very small probability, large value gives you 1, but typically you just have, like 0 or around 0, these values, right? So if you think about like what's the meaning of this, so this asks what is the probability of seeing the state action pair under my target policy compared to seeing that under the logging policy. Well, it's most of the time it's 0 or near 0. It's like you're gonna see a lot of really small values. And then people talk about like, oh, but this blows up. Like, so what does it mean that it blows up when you typically see very small values? It's kind of like a bad distribution. You see most of the time small values, but occasionally some big value. So when you see that, you will see that when the logging policy, you choose a state action pair, when the logging policy would not go, but the target policy would go, then the reverse happens, but that's not in your data, right? Like, the data is not going to tell you that. And so this is one, like, really challenging aspect of doing all of this. If you want to do things with this density ratio corrections, that your data may not be telling you that you don't have good data. The math can tell you that you don't have good data. But your data could actually be good. But you never know. So there is the related question of, okay, so all of these were about, policy search. But if you just want to do policy evaluation, so you ask a question, I have a batch of data, and I want to know how good this policy is. So we're really focusing on a single policy now. Even the policy class is gone. You don't want a point estimate. You want a lower bound on the value, which holds with high probability. So you kind of want a one-sided interval at least. So in any interval, the variance is going to matter. So what's happening with the variance here? The variance can be really bad because you have these very small probability events when these values are really large. In the variance, these would be squared. So it's just like, it can be really bad. So that raises the question of whether you can ever have enough data to actually get non-trivial lower bounds for the value, even for the tabular case. If you were generating data following a policy, and you want to know whether you have enough data to like claim something non-trivial about, like, can you get a non-trivial lower bound for the value of this target policy? How do you know that you have enough data for that? Is there any priori way of knowing that? And it turns out no. But you can have a stopping rule that tells you that, or it's not really a stopping rule, but like you can have a lower bound that's always valid, but it's going to be invalid for a long time, and eventually it starts to get valid. And the lower bound, you can show that, well, if you do the trivial things again, plug in the rule, estimate the transition probabilities, like nothing really fancy, then that's basically what you want to do. And from that, you can get a lower bound that's essentially unimprovable. Yeah?
Yeah, so, sorry, for this policy evaluation one, are we now limiting ourselves to not being able to choose the behavior policy?
Absolutely, yeah. It's the same setting as here.
But there
I mean, like here we were asking a secondary question of like, if we were given the choice of choosing the behavior policy, could we do something? But in this policy evaluation, it's just like, yeah, you're given a behavior policy and you have a target policy and you just go.
Okay, because the other way it wouldn't be hard, right? I mean, it would just be like an optimal design.
It's the same, yeah, like you cannot choose passively better than the uniform.
Yeah.
It will be the same, right?
Well, wait, just if you could choose the behavior policy and you want to evaluate a policy.
Or you would choose the same, if you know ahead of time what policy you want to evaluate, yes, but if you didn't, then it's just the uniform.
Right.
So it's kind of boring. Maybe if you had set up policies, then they could be sharing some actions, and then you would put more weight on the actions that are shared. It's semi-boring. So there you could do something more clever probably, but probably not too clever.
Yeah. I also looked at the Andrew and G Pegasus paper, and it seems like they were looking at POM DPs with given a model.
And they also generalize because they noticed that you don't actually need to know anything about the state here, because you're just running this simulator. So maybe that's what saw the paper. But the result is really like this.
Yeah.
It's Andrew and Stuart Russell.
Michael Jordan.
Oh, Michael Jordan.
I think this is the one from 2000.
Yeah.
Yeah.
With the
Policy search method for large MDPs and POM DPs.
yes.
Yeah.
Huh? Yes.
Yeah, I was want to ask a clarification about the good data according to the important sampling ratio. Does that mean good data means your logging policy is very like your target policy, so that you have a good coverage over the
Yeah.
state impact.
That's right.
And in practice, you don't know what's the logging policy, so that is the issue.
Oh, well, there are many issues, right? So you're not choosing any of these, so maybe you don't have good coverage. That's one issue. And yeah, like it could be that an issue on the top of this is that you have no idea about this logging policy. Yeah. Right. So here there is a little side story that if you look at these ratios, you might think, oh, this depends on the unknown transition properties, but no, because it's along the same trajectory, so those terms all cancel out, so that's all fine. But it's still, if you don't know the probabilities that are assigned to the actions by the logging policy, then it's like, you can try to estimate that, and then you are in the land of these doubly robust estimators, where they are arguing that even if you're estimating maybe this probabilities, it's not a big deal because the errors that are coming from this are lower order. So the statisticians have also been looking at this problem, and they are most of the time looking at asymptotic efficiency, which is like asymptotically how small the variance is. And focusing on this, you can run some relatively simple analysis, and you will see that if you have, like products of estimates, then you have the true value plus error, true value plus error. Then there are the cross terms where there is only one error term and the true value multiplies. And there are the error multiplied by error term. That's a lower order term. So if you can estimate at the rate of 1 over root n one value and another value at the rate of 1 over root n, the product of the two estimates is a good estimator for the whole thing, and it didn't introduce any additional complications. So because of this, yeah, you can estimate even these probabilities, that's fine. It's a bit messy, but asymptotically it works out. Finite time, no. I think maybe there is room for improvement for this, the finite time case. And then we are back to the land of the pessimistic algorithms. So people are trying to argue that the pessimistic algorithms are the best choice for the finite time case. Whenever you see such a paper, you should ask yourself, will the plugin estimator get the same bound if I work hard? And if you don't know the answer, then okay, the status of the result is unknown. But for most of the cases, the answer is yes. So it's not a solved case. All right, we had one more question on Slack. Who was it?
Humayun? I don't know if he's here.
Okay.
So,
Maybe you
I can read it.
Yes.
He says, I'm trying to understand how batch RL relates to other parts of RL. Is batch RL synonymous with offline RL? Is an online method that collects a batch of data and learns a model from it not batch RL? Or is batch RL the opposite of learning incrementally? Would the plug-in method still apply if the model is estimated incrementally without collecting a batch? Maybe I should ask each one of these independently because there's a lot.
I think this is a long and windy question. Yeah, let's go one by one.
Yeah, so I think the first one is batch RL synonymous with offline RL? That's a good one to start with.
Yeah, okay, so there is a relationship, there is an overlap in terms of the techniques that people use. The algorithm design question is, batch RL is a problem setting. Offline RL is focusing on algorithms that are estimating various quantities from data. So it's like pretty much synonymous, if you wish. Here I'm trying to make a case for that we should distinguish between problem definitions, problem settings, and just I don't know, algorithmic tools. So many times it's not very clear to me where people talk about offline RL. What is that like? I don't know what offline RL is. Okay, like intuitively it means that, or off policy, maybe even off policy, right? Like it kind of means that you have the wrong data and you still want to run your estimation or optimization algorithm.
Yeah, well, I'm a little confused actually. So, what is the problem setting that offline RL deals with that is not formally like used in?
I don't know. Like people use these terms and offline RL. Maybe it's the same.
Or I guess
No one ever defines these terms. Like I'm trying to define these terms, and so that's
Yeah.
why a lot of times when you ask me like, "Oh, is this Z design?" No, I made it up, but yeah, offline and real. It's the vibe is the same.
So there's three things. There's batch RL, there's online RL, and there's planning, basically. Oh, that's
Yeah.
in the middle.
Right.
But offline RL doesn't like.
But you can call batch RL offline
Yeah.
RL if you want to.
Okay.
I think.
Yeah, the next one is an online method that collects a batch of data and learns a model from it, not just batch RL.
So it could be batch RL algorithm. It's not batch RL.
Yeah. I guess it collected it online.
Was it collecting it online?
It says is an online method that collects a batch. Okay, sorry. Is an
No.
online method.
Yeah. So
That
you could
collects a batch of
increment.
data.
So I think that the follow-up question was, for example, if you build a model incrementally, like,
Yeah.
is it considered batch RL? Yeah, the problem setting is batch RL, and then you can have many different algorithmic ideas that aim at addressing the batch RL problem, and one would be to incrementally estimate a model, and that's totally fine.
Yeah, the
It's like an
follow-up one
algorithm.
is batch RL the opposite of learning incrementally?
No, absolutely not. So, yeah, okay, so I guess there is a bit of a confusion in the machine learning literature there, because I think the neural network people would sometimes call algorithms which are not incremental, just batch algorithms.
Yeah.
And that's not the usage of the term that I'm with.
I guess here, yeah, the incremental part is referring to like learning after each time data is gathered.
Right. Yeah.
Where here it's like a giant chunk of data is gathered,
Right.
and there's learning. So
Right.
there's one step. It's one increment
Right.
in this view.
Yeah.
Yeah. Okay, and then the last one is, I guess, would the plug-in method still apply if the batch, or if the model is estimated incrementally without collecting a batch?
Sure. You can write the estimation in an incremental fashion. Doesn't change the result.
Yeah, I guess the only thing that changes is the policy. Well, you can just follow the same policy you were following before, and you
Yeah.
can change it. As long as you don't update the policy, then it's the
It
same.
can be, like exactly equivalent.
Yeah, yeah.
The output, the policy is the output, and they can be exactly the same. If things are set up in a nice way, and if you have a lazier incremental method, it messes up a few things. Maybe it's not going to matter much. Yeah.
Yeah, that's useful.
I think, yeah, especially this batch, batch is used in many ways. And actually maybe thinking about, we already have online RL, so then why did I not call this offline RL? I don't know. I guess in the literature it was called batch RL first.
Yeah, because I think some papers do use offline RL.
Yeah.
And then I was thinking the same exact question recently. And I was like, this is exactly the batch RL setting that they're talking about here.
Yeah.
Okay.
I think on offline IO makes sense in a deployment time, just like Albert's question, like companies can't put the algorithm online and they collect the data and learn offline. That's how they use the word.
Right.
And consider the interaction mode between the algorithm and the environment. And batch IO is more general than offline IO. That it can also like have some interaction parts.
Right. Yeah. I don't know. Yeah, this terminology is hard. It's a mess. It's hard in the sense that, like, okay, it's easy, it's just words. Like we define their meanings, but the field hasn't converged on a single set of definitions, and
We need a textbook.
I think we will soon have the problem of having multiple textbooks defining things differently. So, watch what you're asking for. It's, yeah.
Yeah, because I guess in supervised learning, the batch term is usually you like gather a batch, then you train, and then you increment the
You even have a
batch.
mini batch or something,
Yeah, yeah.
and
Where here it's like your batch is the full. You get it's like what do they
Yeah.
call it in supervised learning? Where your batch is the size of the data set, the whole data set.
right.
I don't know. Yeah.
Offline wouldn't be a bad word either. Okay. No more questions? We're good.